So, as sir has already told that I'm a Dr. Vikas.
Before that, I did my PhD from IIT Guwahati, and then I did my postdoc from IIT Bombay, and sometimes I also spent at NTU Singapore. Thereafter, I have been enrolled here as a assistant professor. So just today, in the today's session, just I am going to brief you how to use the tool Abacus in order to solve the problems, whether it is related to the polymers, whether it is composite, metals, and anything else. Just basics, fundamental will be the same, and procedure will be maybe the different. And we can also ensure like there are several softwares that is dealing with the finite element methods or finite element based things. That is ANSYS is there, Abacus is there, Simulink is there. Thereafter another software SysWeld is there. So a lot of softwares is there that is handling the finite element methodology behind the screen only. It may possible that implementation procedure is different and it varies from the one software to the another software. So we'll just try to brief from the basics so that you people would be able to track that, means how to use the Abacus tools and all. If you are new user about it, if you are not having the any expertise or you didn't handle those things since your PhD or postdoc, whatever. So how many of you are aware of the Abacus or finite element method? Okay, one guys. Any other? Okay. So better means just I will move towards the interface of the Abacus, and I will start from the beginning. So how to deal with, means how to start to fabricate the product and how to implement the tool and all those things. So that will be much better. Just I will give you the brief ideas about what we can do actually by using the Abacus tools. So see, this is the one development that I did in the recent past, that is development of the model related to the additive manufacturing, whether it is for the case of polymers or whether it is in the case of composite, but it is devoted towards the metal only. So these are the procedures that I have followed during the implementation of deposition process within the Abacus. So that is firstly, since my problem was to fabricate this solution domain, that is the fabricated structure, means this is the cuboid that we have that we need to print by using the laser deposition process. Okay, so this product we have to make, okay, by using the Abacus software. So that's why we have created a firstly solution domain or a geometry kind of thing. Thereafter we have implemented the material property in order to give the behavioral aspects of the material, specific material towards this fabricated structure, that is density is there and thermal conductivity and specific heat capacity. Thereafter latent heat of fusion is there, solidus temperature and the liquidus temperature. So these are the physical properties, or we can say thermophysical property, that is playing a role if you are thinking of heat conduction equation or thermal analysis. So if we are thinking of doing thermal analysis, whether it is building process, whether it is deposition process, or whether it is temperature assisted any process, whether it is machining or something like that, since temperature is coming into the picture. So in order to model the temperature or time temperature history, just we have to do the thermal modeling. So that's why these properties, incorporation of these property within the Abacus software is very, very important. Otherwise they means whatever product we are going to make, that will not be able to give the specific features that will be which we expect from in the physical phenomena or in the practical environment. So thereafter after creating the solution domain, we have given the material properties or incorporation of several properties, thermophysical properties. Thereafter we have implemented the thermal or mechanical boundary conditions, since we are dealing with the thermal modeling. So there is no any requirement of the mechanical right now. Later on in the mechanical analysis we will take care of this thing. So thereafter we have implemented the thermal boundary condition. Thermal boundary condition, in the case there are three aspects of the heat conduction, means heat diffusion from the material, that is one is conduction, another one is convection, and thereafter radiation is there. So all three coming into the picture if we are taking care of the temperature assisted things. So that's why if we are dealing with the melting temperature, since deposition is going on, so that's why we have to deal with that melting temperature of the material. So at that point of time only these three mode of heat transfer will be there, that is conduction, convection and radiation, and that will come into the picture as a thermal boundary condition. So we need to incorporate these three boundary condition. That associated equation I will show you in the later on. Okay, thereafter whatever boundary condition we are implementing, thereafter we have to deal with the thermal load. Means whatever deposition we are making, means suppose laser beam is there, or means if we are welding, then welding source is there or heat source is there. So in order to replicate those heat source, just we have to give the Gaussian heat flux, means heat load will be there. Okay, and this is in the form of double ellipsoidal. See, this is the one kind of heat source that I have incorporated during the welding or deposition process. Okay, different heat source is there, that is double ellipsoidal is there, single ellipsoidal is there, volumetric heat source is there, hourglass model is there. So depending upon your geometry, whatever you are getting during your in the experimental setup or in the experimental fabricated structure, on the basis of that you have to track or you have to select the heat source model. So on the basis of my deposition or welding process, just we got that, means by using the heat and trial method, we got that double ellipsoidal method is more predominant and can give the reliable result in the case of laser welding or laser deposition process. So that's why we went for the double ellipsoidal model. So on the basis of this, we have for incorporation of this double ellipsoidal heat source model, we have incorporated a deflux uses subroutine. Subroutine in the sense that means Ambedkar software is there, and within that we have to generate one extra file by using the Fortran language code, because in the Ambedkar there is no any heat flux module is there. Okay, so if we want to migrate our heat source from one position to another position, means traveling will be there, means velocity will be there. So for the incorporation of these velocity aspects, just I have given this flux or heat source by using the subroutine only, that I will show you. So how to incorporate the subroutine and all. So Gaussian heat flux we have incorporated in order to impinge the heat source during the welding, or we can say during the deposition process. Okay, and thereafter, since we are dealing with the additive manufacturing, so element date and birth is most important, because at the position where we are giving the heat source, at that position only material is depositing. So it means that wherever heat flux will be there, just element activation will be there at that position only. So that's why we have also taken care of the element date and birth analysis, means the position where we need to give the laser source, there only the material deposition will happen. So on the basis of that, we have incorporated the element date and birth technique, and by using those things, whatever, since we are dealing with a lot of material deposition, see, we have to make this product, and if suppose this is of 10 into 10 into 10 mm, so, and we are depositing the one layer of micrometer only, so a lot of layer will be there. So it is too hectic things to deal with a lot of layers if we are going for the manually in the Ambedkar. So that's why we have generated the we can say in-house developed the Python script in order to deal with a lot of layers in a one go. So for those things, to get rid of all those things, just we have generated the Python scripted interface, and finally whatever result we can get from this model is transient temperature field. It means that transient temperature field means temperature with respect to time. Means for this model, for each and every node we can get the time temperature history. Okay, so for whole the model. Now on the basis of the time temperature history, what we can actually calculate? So this GR calculation we can do on the basis of this transient temperature, which whatever output we are getting from the thermal analysis. So what is G and R? G is basically temperature gradient. Okay, this is the solidification parameters, right? So solidification parameters is very important if we are thinking of each and any product right, by using the deposition process or any other things. Okay, but if we have to deal with the temperature assisted any process, just we need to take care of the GNR, means solidification parameters. That is very crucial in order to predict the microstructure as well as predict the mechanical and functional property also, whether it is tensile testing things, whether it is hardness, whether it is microstructure, metallurgical properties, any other thing. So we need to take care of the solidification parameter, and that is G and R. G is the temperature gradient and R is the solidification rate, and if we are multiplying these two factors, then we can be able to calculate the cooling rate only. Okay, solidification rate into temperature gradient, that will give you the cooling rate, and cooling rate will decide the microstructure of the material, whether it is composite or whether it is metal pure, whether it is alloy or whether it is polymer also. Means if we are thinking of the polymer based matrix, so microstructure come into existence there also. So whatever microstructure you are going to get, so that depends upon the G and R value. क्या हो गया?